In your school class, you have learned that Ohm's law, that temperature and other physical quantities remaining constant, the current flowing through a conductor is directly proportional to the potential difference between its ends, and we write the law in mathematical form is this. And we further found that the resistance depends on the geometry of the conductor, that is, it is directly proportional to its length and inversely proportional to its cross-sectional area. And we write the law in this form, where rho is called the resistivity, where resistivity is numerically equal to the resistance of a conductor in the form of a unit cube. It is the property of the material of the conductor. If we rewrite this equation, we can rewrite this equation as V by L on the left hand side, and on the right hand side I write rho by A. So this is V by L is the potential difference across the length L, so it is a measure of electric field, the magnitude of the electric field, and this is current per unit cross-sectional area, so this is the current density, or we may write it as J is equal to 1 upon rho times E, we call it sigma E. This is the resistivity and this is known as conductivity. Reciprocal of resistivity is known as conductivity. So this is the alternative form of Ohm's law, or we write in vector form J is equal to sigma E. So this is Ohm's law in modern language. We shall the resistance. So the resistance depends on the conductivity of the material. The higher the conductivity, the lower is the resistance, and furthermore it also depends on the geometry of the conductor. Here we shall consider few cases to show how the resistance depends on the geometry of the conductor. As the first example, we consider a conductor in the form of a cylinder, and the current is flowing along the axial direction of the cylinder. So we consider this is the form of a cylinder. It is a cylinder of length L, and the potential difference between its ends is this V. Since the current is flowing, this is the axial direction, and the current is flowing in this axial direction. So it is a higher potential region, this is a lower potential region. So first is the axial current flow in a cylindrical conductor. This is the example. So the potential difference is this. We start with the Ohm's law, that is J is equal to sigma E, and for J, if I is the current flowing and this cross-sectional area is A, then J is equal to since I is equal to J by A, J is equal to I times A, conductivity, and E is V by L. E is V by L. So we write V by I is equal to resistance J is the current density, is the current per unit area. So J here I have done a mistake. This should be I by A, and so that V by I is equal to sigma O by A. So this is the resistance which depends on the geometry as well as on the conductivity. This is just the case we have considered in the development of this relation. Now, as the second example, we consider the radial flow of current across a hollow cylindrical conductor. Let me first write the geometry. We have a hollow cylindrical conductor which comprises of this is an inner cylinder of radius A and this is an outer cylinder of radius B. This is the solid part or the conducting part, which this hollow cylinder is made up of a conductor of conductivity sigma, and the current is flowing from inner to the outer cylinder. So if we take the sectional view, this is the inner cylinder and this is the outer cylinder, and current is flowing radially outward from inner to the outer cylinder. This is the geometry. This much is A and that much is B. So for example, radial current flow in a hollow cylindrical conductor. So if we consider this region, that is the region in between the two cells, that is within the material, then we can find out the electric field in this region using Ampere circuital law. If we assume the Gaussian surface as a cylinder, coaxial with the axis of the hollow shell and of radius S, where S lies between B to A. So this is in between the cell. Then we, if we apply Gauss's theorem, this is E dot ds is equal to Q enclosed by epsilon 0. So on the left hand side we have the area of the Gaussian surface. The area of the Gaussian surface is 2 pi s times L, where we have considered a Gaussian surface like this. This much is S and this much is L. Length of the Gaussian surface is L. So times E is the electric field times lambda L epsilon 0, where lambda is equal to charge per unit length of the inner cylinder. Or we get E is equal to lambda upon 2 pi epsilon 0 s, and so far the direction is concerned, the field everywhere is radially outward, so it is in vector notation, it is S cap. So this is the electric field. If we We want to find out the current density. The current density J J is governed by sigma E. So J is this is the current density. So the total current is flowing across this. So the current that is flowing, if we consider the what is the total current flowing, it is J dot ds. The current is flowing across the curved surface of the cylinder, that is it is flowing across rho s is equal to constant surface. So this is equal to s cap s d phi dz, where we have used the coordinates Cartesian cylindrical coordinate system as this, and for instead of rho I have used s, so that no confusion arises with the conductivity resistivity. So this is our cylinder. So we write for J from this expression, it is the constant parts are taken out, epsilon 0. Then within the integral sign, the integration will have s cap by s dot s cap s d phi dz. So this part contributes nothing, phi integration contributes 2 pi, and z integration gives the length L. So this is equal to sigma lambda 2 pi epsilon 0. From this part it is 2 pi, and from dz it is L. So all together it is 2 pi cancels out, lambda sigma L upon epsilon 0. So this is the current. Let me write the current as this. Current flowing through this is epsilon 0. Now we are to find out the potential difference. The potential difference has to be evaluated using the law that E is governed by the gradient. So it's not no more required. E is equal to minus del V del S, and the inner cylinder is at a higher potential and the outer cylinder is at a lower potential. So we get dV is equal to minus EDS. E dot ds, if we write it in the vector form, so dv is equal to actually E is equal to minus grad v, where from we can get dv is equal to minus E dot dr. In this case the current is flowing in radial direction, so it is E dot dr, where dr is s cap times ds, because the length element in this direction is s cap ds. So this is written, and for E we write, for E is governed by this minus lambda 2 pi epsilon 0 and S cap by S dot S cap ds. So the result is minus this is the expression for dv. So we get v by integrating it with proper limits, and on integrating we get it as this function will be log function, and this will be lambda upon 2 pi epsilon 0 log of b by a. Now, so v is this. Resistance R is defined as V by I, so this is lambda by 2 pi epsilon naught log B by A so this comes out to be lambda cancels out and epsilon 0 cancels out. So the result is log B by A 2 pi sigma L. So this is the expression for resistance for the radial current flow across a hollow cylindrical conductor. You see that the resistance is inversely proportional to the conductivity and depends on the geometry of the conductor. As the last example, we consider the radial flow of current across a cylindrical conductor. Hollow spherical conductor of inner radius A and a outer radius B. Just the case that I have considered here is the cylindrical hollow conductor. Now I am going to consider a spherical hollow conductor. Hollow spherical conductor. So the conductor we consider is this. This is the conductor of inner radius A, and this there is another conductor concentric to it of radius xb, and the current flowing radially outward. So this is the radial current flow direction. If we consider first we consider the electric field. If we consider the electric field in this region, that is for R in between V and A, for R less than equal to B greater than equal to A, that is within the material having conductivity sigma, we can find out the electric field using Gauss's theorem. So this part is E dot ds is equal to Q by epsilon naught, where Gaussian surface we consider a sphere concentric to the shell and having radius r. So this is 4 pi r square E. 4 pi r square E is equal to QA by epsilon, or where QA is the charge in the inner inner conductor. Charge in the inner conductor. So E is equal to QA by 4 pi epsilon 0 r square, and the direction is along r cap. So this is the direction. This is the direction of the vector, and if we want to find out the J, the current density, say the total current flowing I is equal to J dot ds. Here the current is flowing across the spherical surface, that is R is equal to constant surface, so it is sphere. So we write it for J, we write the constant part outside, QA sigma 4 pi epsilon naught within this r cap upon r square, and this is the R is equal to constant surface, so this is r square sine theta d theta d phi, so and times r cap, so dot r cap r square, and this part is the solid angle d omega. So when you integrate it, gives you 4 pi. The result is simply 4 pi, which cancels out with the 4 pi of the denominator. So this is QA sigma upon epsilon 0. This is the current. Now we come to the potential difference. As in the earlier case, potential dV is given by minus E dot dr. Here r is along the radial direction, so we write minus for E is, this is QA r cap, QA r cap by 4 pi epsilon 0 r square dot r cap dr. So this is equal to minus QA upon 4 pi epsilon naught dr upon r square. Now if we integrate it, the inner shell is at a higher potential and it is at a lower potential, and if we integrate it with limits, we get the potential difference. This is the potential difference between the inner shell to the outer shell. It will be so if we consider the resistance current, the current value of the current is this. QA and epsilon 0 cancels out, so this is the resistance for the radial flow of current across a conductor in the form of a hollow spherical cell. Now we come to the conclusive discussion on electromotive force or EMF. In electrostatics, we know that the electrostatic field is a conservative field, so its curl is 0. And electrostatic field may have its space dependence, but it does not have any time dependence. So we first take electrostatic field. Electrostatic field is denoted by E of as a function of R, no time dependence, and it has curl E is equal to 0, conservative force field. But whenever we consider a circuit, then with a source of EMF, we have a source of EMF, then a current flows in the circuit. So there is some agency which drives the current through this, and we find that we define EMF or electromotive force as the force per unit charge. This is the force per unit charge, and there is a work done along a closed circuit. This is the definition of EMF. So it is the tangential component of the line integral of the tangential component of the force acting on unit charge. So if we write it in terms F by Q is electric field, then this expression is simply becomes E dot dl. Obviously this is not an electrostatic field, because had it been an electrostatic field, the EMF would be 0. So this is there are contribution other than static electric field. Even if you include the electrostatic field within it, the electrostatic field will ultimately not contribute to the EMF. So this field must not be static field, so it should have time dependence. So this is electromagnetic field, so as to say electromagnetic field. This electromagnetic field may arise due to several reasons. One of the reasons is the chemical effect. If we consider HCl dissolved in water. When HCl is dissolved in water, then it dissociates into H plus ion and Cl minus ion. Then this hydrogen ion, positive hydrogen ion, being lighter, they diffuse much faster than the chlorine ion. So there will be a diffusion of H ions from a region of higher concentration to a region of lower concentration, and the electric field will be generated, which is one of the contribution to the dynamic field. This electric field or electromagnetic field, so to say, may also arise due to the relative motion between a closed current loop and a magnetic field. As for example, consider the movement across a ring. A ring is placed in a time varying magnetic field, fixed ring, and it is placed in a B field, which is a function of time, and it is placed in a B field. Then it is found that the certain flux is linked with it, as we shall discuss it in connection with electromagnetic field. So this changing time dependent magnetic field induces some current or electric, and so to say electric field in the fixed circuit. This such a EMF, induced EMF, is called transformer EMF. Which arises due to time dependent magnetic field. Another thing that may happen, that we have a B, constant B, and a circuit is allowed to move, a circuit allowed to move in this field. A circuit moves in a constant magnetic field. Then the charges that are within this current carrying conductor experiences a force, and this force is of the form V cross B dot dl, and it is integrated over the contour. This is called a motional EMF. So these are the few examples of EMF which we shall consider in detail in connection with the Faraday's laws of electromagnetic induction.